Magnetic levitation, Maglev, is an advanced transportation technology in which trains are lifted and propelled using magnetic forces. Unlike conventional trains that rely on wheels and tracks, Maglev trains float above the track, eliminating friction and allowing for exceptionally high speeds. This technology relies on two primary types of magnets, electromagnets and superconducting magnets. The basic principle of Maglev involves the use of electromagnetic suspension, EMS, or electrodynamic suspension, EDS. EMS systems utilize conventional electromagnets to create a magnetic field that lifts the train a few centimeters above the guideway. This method requires precise control of the magnetic forces to maintain stability and ensure a smooth ride. EDS systems, on the other hand, use superconducting magnets cooled to extremely low temperatures to achieve levitation. As the train moves, it induces currents in the guideway, creating a magnetic field that repels and lifts the train. Maglev technology offers several advantages over traditional rail systems. The absence of friction between the train and the track allows Maglev trains to achieve much higher speeds. For example, the Shanghai Maglev train in China operates at speeds of up to 431 km per hour, 268 miles per hour. Additionally, Maglev trains are quieter and produce less vibration, leading to a more comfortable passenger experience. The reduced mechanical wear also translates to lower maintenance costs and longer lifespans for both the trains and the tracks. Despite these advantages, the widespread adoption of Maglev technology faces several challenges. One significant hurdle is the high initial cost of infrastructure development. Building the specialized guideways and implementing the necessary electromagnetic systems require substantial investment. Moreover, integrating Maglev lines with existing transportation networks can be complex and costly. There are also technical challenges related to maintaining the superconducting magnets at extremely low temperatures, which can be energy-intensive and expensive. Currently, Maglev technology is in operation in a few locations around the world, most notably in China and Japan. The Shanghai Maglev train, operational since 2004, connects Pudong International Airport to the outskirts of central Shanghai. Japan has been developing the Chuo Shinkansen, a Maglev line intended to connect Tokyo and Nagoya, with plans for future extensions to Osaka. This line aims to reach speeds of up to 500 km per hour, 311 miles per hour, significantly reducing travel time between cities. In conclusion, while Maglev technology presents a futuristic solution for high-speed travel, its implementation is hindered by substantial economic and technical challenges. Continued advancements in materials science, electromagnetism, and energy efficiency will be crucial for overcoming these barriers and realizing the full potential of Maglev systems in the global transportation landscape. Description for much more.